Okay, so in class today, we worked on deriving the derivative function, and not everybody got all the way through it. So I wanted to help you with the consolidating of your understanding on this. So the first parts, you had to plot a point A and a point B, and you had to figure out what was the slope of a line connecting A to B. And we were comparing it to the tangent slope. So at point A, if I were to draw in, and of course now I've misplaced my straight edge, so let's use this. Here's point A, and if I was to find the tangent, I would want this to just touch at point A, not go through any other points, but only at that point. So I can draw that in, and if I estimate the slope of that line that is tangent at point A, that would have a slope of 2. So that means at point A, the rate of change right there is 2, let's say, feet per second. Okay? So right here, the rate of change happening at this point, according to the tangent line, is up 2 over 1. I'm going up 2 feet every second if this was feet per second. Okay? So my rate of change is 2. Now, if I put on my point B, so 2 and 4, that clearly is going to have a different slope. If I combine A to B, it's going to give me a different slope. It's not going to give me 2. It's going to give me 3. So if I find the slope between A and B, I'll find that it's 3. So they're not the same. They're not terribly different, but they're not the same. So the steps through this is we start moving point B closer and closer to point A, and as we do that, you should notice that the slope of AB is getting closer and closer to the slope of the tangent line. So as I move this point B closer and closer to point A, I'm getting a lot closer to the slope of the tangent line. Now, why is this significant? It's significant because the tangent line, all I can do is sketch that in and hope that I hit some points that I can use to help me find that slope. So as we saw in class when we were doing it with the ball, the graph of the ball flying through the air, we were getting wildly different slopes. Each group was getting different answers. So it wasn't very consistent, it wasn't very precise. So drawing in this tangent line and trying to figure out its slope, which gives us the rate of change at that point, is really hard to do. So what we are looking for is we're looking for a more precise way of figuring out what is the rate of change at one single point. Okay, so when you walk through these, you notice that point B was getting closer and closer to point A each successive time. So what do you notice, and what does this remind you of? This should remind you of a limit. Okay, we're getting closer and closer to the slope of the tangent line. So as we move point B closer and closer to point A, so here let the x value be 1.001. I mean, that's like practically right on top of point A. So as they get physically closer and closer to each other, we're getting closer and closer to the actual slope of the tangent, which is the instantaneous speed. Okay, so that's what you should notice. And what does this remind you of? It reminds me of a limit. I'm getting closer and closer and closer to a given value. Okay, so now on to page 3. Instead of using exact points on a graph to find the slope of a tangent, we would like to have an equation that can tell us the slope of the tangent line at any point. Okay, we don't want to have to do all these calculations and figure out how close can I get? What's close enough? We want to be able to figure out what is the slope at any point on the graph. Because right now what we're doing is we're only finding out the slope of the line right here at 1, 1. But what if I wanted to know the slope of the line over here at 3, 9? Or over here at -2 and 4? What if I wanted to know the slope here? Okay, doing this repetitive, getting closer and closer and closer and seeing what I'm approaching is kind of cumbersome, kind of time-consuming, and prone to errors because we have to make so many calculations. Okay, so what we want to do is we want to come up with one equation. We want to write an equation that can tell us the slope of the tangent line at any point on our equation. And we are going to be able to do this. It was first done by Newton and Leibniz, and now we're going to do it. So the equation is called the derivative function. Okay, so the derivative function is an equation that we can use to find the slope anywhere on our graph. If we know the equation of our graph, if we have its equation, we can find the slope, the instantaneous rate of change, or the instantaneous velocity, anywhere on this graph without having to draw a single tangent line. So we want to find this equation. So we're going to find it. So to find the derivative function, we will repeat the above process of finding slope, but we're going to do so with variables, okay? No more numbers. Instead, we're going to use letters. We're going to generalize. We're going to find a general formula. First, we need to identify the letter H in parts A, B, C, and D. H is the change in x, the horizontal change. So how far apart is point A and point B in the x direction? So from point A to point B, what's my horizontal distance? It's 1. Okay, from here to here, the distance, the change in x is 1. So that means my h value is 1. Okay, so the x-coordinate of B was 2, the x-coordinate of A was 1. I subtract those, I get 1. So the difference between here and here, that's my h. How far do I have to go from here to get to here? I'm adding h. So in this case, h was 1. So what about in point B? So if I look at B, my x value was 1.5. So here's 1. Then my x value was 1.5, and whatever my y value was. But how much bigger is that x value? It's 1.5 right here minus 1. What's that horizontal distance? That would be 0.5. So to get that, I have 1.5 is my x value on point B minus the x value on point A, and that gets me 0.5. Okay, they're half, where am I? Half a unit apart on the x, just looking at the x. Okay, part C, sorry. On part C, x is 1.125. Okay, so I'm comparing that to the x value of point A. What's the difference there? Well, it's 0.125. So that means my h value here is 1.125. And then what about on point D, part D, sorry. Part D, it says 1.001. So what's the difference between these? It would be 0.001. We'll fill that in. So this one is 0.001. Did I do that right? Yeah. Okay, notice that as h got smaller, see, here's my h. This is h is equal to that. This is my h. This is my h. How far to the right of point A is point B? It got smaller and smaller and closer to point B. Let's see. Sorry, let me read that again. Notice that as h got smaller, the closer point B got to point A. Okay, so that B got closer and closer, and so my h is getting smaller and smaller. So if point A is x and f of x, then point B is whatever that x value was plus the difference. And then to get the y, well, we got to take this x value and plug it into the function to get my y value. Okay, so that's what we did over here. So once you know what your x value is, you can plug it into the function and figure out your y value. Right, that's what this is saying. Okay. Now, with the function f of x equals x squared that we used in parts A through D, point A is at x and x squared. Okay, so this is x. If I square 1, I get 1. Okay, so this comes from here. If I plug in 1 for x, 1 squared gives me 1. So another way of saying that is this is 1, this is 1 squared, or this is x, and this is x squared. So we want to state in general, how can we write point B in general? So the x value is x plus h, because it's whatever the A point was, whatever the x-coordinate of point A was, plus a little bit more. And then to get the y value, what did we do? Well, we plugged it in here. We would plug in our x value. So here's our x value. We would plug that in here, and we would square it. Aha! There it is. Okay? So I take my x value, here's my x value, I plug it in for x, and that gets me my y value. Okay, now we're going to substitute this into the slope formula. So to find the slope at a given point, A, I would need another point, B, and then I would minus the y's and minus the x's. So my y's are here and here. Okay, we usually start with the one with the bigger numbers, which is going to be the b. So we're going to start with the b. We're going to start with this one. So this would be x plus h squared minus x squared, because those are my y values. Here's y and here's y. And then on the bottom, I'm going to minus my x values. So x and x. So I'm going to have x plus h minus x. Now let's see if we can simplify this. So this is where our warm-up comes in handy, because I asked you to do this substitution and simplify it. So we went over this in class. So x plus h squared, we'll go ahead and do it again. X plus h squared is equal to x plus h times x plus h. If I multiply that out, I get x squared plus hx plus hx plus h squared, which is x squared plus 2hx plus h squared. So that's this. So I'm going to go ahead and do it up here. So this part is x squared plus 2hx plus h squared minus x squared. And in the denominator, I've got x plus h minus x. Now I can simplify that. Let's simplify my numerator. I've got x squared minus x squared. So those cancel out. And I'm left with 2hx plus h squared. And on the bottom, I have x minus x. Those go away over h. Okay, I can simplify this some more. I notice all the terms have an h. So I'm going to factorize the numerator. I'm going to pull out that h that they both have in common. And what's left behind is 2x, because h times 2x is 2hx. Plus h, because h times h is h squared, all divided by h. Now that it's been factorized, I can reduce, because it has to be a product of number times number in order to reduce. I can reduce my h's, and I'm left with 2x plus h. So this is a formula that can tell me my slope. This is my slope. Okay? So now, it says, remember that h is the horizontal distance from A to point B. And we want this distance to be as small as possible. Okay, so right here, if I were to plug in my h, see my h for right here was 1. If I plug in my 1, and then my x value was 1. If I plug in 1 and 1, 2 times 1 is 2, 2 plus 1 is 3. That would give me a slope of 3, which is what we got when we found the slope between A and B. So when the h value between A and B was 1, we got a slope of 3. So that works here. 2 times the x value, 1, plus the h value, and h was 1 on this one. Okay, the h value is the difference from A to B along the x-axis. That was 1. It gives me 3, which matches what we did when we did it visually. Okay, but now we're going to take this a step further. Remember that h is the horizontal distance from A to point B, and we want this distance to be as small as possible. So remember, we started with it at 1, but then we did 0.5, and then we did 1.125, and then we did 0.001. We wanted h to get smaller and smaller and smaller. And what does that remind us of? A limit. We want the limit as h goes to 0. We want h to become 0. Oh, and look at this. Hey, that matches what I did up here, right? But look, we simplified it further, because if we try and plug in 0 right now, we're going to have to divide by 0. So this is why we did all that work with limits, so that we can actually now simplify this and figure out what is our derivative function for this equation. All right, so what we're going to do is we are going to go ahead and I'm going to copy this down, or actually let's do the whole thing. I'm going to factorize just just like we learned before, reduce my h's, I'm left with 2x plus h. Now, I'm going to evaluate it as h goes to 0. So I'm going to change h to 0, so 2x plus 0 leaves me with 2x. So this is the equation of a line tangent to the function f of x equals x squared at any point x on the function. So I can use this to figure out what is the slope at any point on my function. Okay, we're going to see that on the next page. Right, so my equation is 2x. 2x will give us the slope. This will give us the slope at any point on that function. So let's go have a look. We're going to put that to use over here. So it says evaluate the equation m equals 2x. Oh, I should have written that over here. M equals 2x. Okay, that's going to get us the slope. So what happens when x is 1? So what is m? M is equal to 2 times 1. So m is equal to 2. So it's telling me that the slope of the line tangent to the curve when x is 1 is going to have a slope of 2. So check it out right here. Here x is 1. I'm on the graph. And if I draw in my tangent, is the slope 2? Up 2 over what? It sure is. What about at negative 2? So I'm going to have slope is equal to 2 times negative 2. So I'm changing my x to negative 2. I get the slope is equal to negative 4. So at negative 2, here I am on the graph. What if I draw in my tangent? Does it look like it's negative 4? 1, 2, 3, 4 over 1. It sure does. It matches. This has a slope of negative 4. This has a slope of positive 2. All right, what about when x is 3? The slope is equal to 2 times 3. The slope is equal to 6. So right here, if I draw in my tangent, is it 6? 1, 2, 3, 4, 5, 6 over 1. Yep, it matches. The slope is equal to 6. So this is our derivative function, okay, our slope function for the graph f of x equals x squared. So this is the graph of the parabola, but this is the equation for the slope anywhere on this parabola. So what do we notice? We notice that the slopes match the slopes of the tangent lines. So the results, what do we notice? The results from the, what do we call it again? We call it a derivative function. Results from the derivative function, give us the slopes of the tangents to the curve, or parabola in this case. Okay, so they match up. The equation of the slope of a line tangent to a function is called the derivative function. And the notation looks like this. Okay, so the equation of the slope of the line tangent to a function is called the derivative function. Okay, and this also gets us instantaneous speed. Right here, how fast is it moving? It's moving 2 units per second. Right here, it's moving 6 units per second. Over here, it's moving down 4 units per second, so negative 4 units per second. Okay, and this is the notation for it. So instead of writing f of x, we put a little prime, f prime of x. Or another way is dy dx. So you might remember I mentioned this in class. dy dx, that's change in y. That's the same as change in y over change in x. And it's when the change in x is approaching 0. Because remember, we said the change in x is going to be h, and we want h to approach 0, because we want to know what exactly is the rate of change right at that particular point. So I want another point that's really right on top of it, and so h is approaching 0. Okay, so dy means change in y, and dx means change in x. And this is another way of writing it. So you'll see these used interchangeably. So if we go back up here where we wrote m equals 2x, The way we would really write that is we would write, let me put it up here, we would write f prime of x is equal to 2x. That's how we would write the derivative function. So this is the same thing as this. Okay, and so we use f prime of x when the original function is given to us in function notation form, and we use dy dx when the original equation is given to us in y equals form. So just like we know that like y equals 2x plus 1 is the same thing as f of x equals 2x plus 1, the derivative function, the one that helps us find the slope at any point on this one, you know what, let's make this a little fancier. Let's make that cubed. Because we already know what the slope was on that one. So the derivative function for this one, we would write dy dx. The derivative function for this one, we would write f prime of x. Okay, so this is the notation we use if we're given it in y equals form. This is the notation we use if we're given it in f of x form. So this gets us our, basically our slope at any point. All right. So now we're going to put this into our notes, and I'll use some more formal wording and clean this up a bit to put it into our notes. But basically now we have a way of finding an equation like this that will help us find the exact rate of change at any point along a curve. As long as we know the equation of the curve, we knew this one was f of x equals x squared, we can find an equation that will help us find the tangent at any point on that curve. All right, notes are next.